group under multiplication, abelian or non-abelian, that we are not saying. If they form a group under multiplication, such a ring is called a division ring or a skew field. That is, it's not necessarily a field. It may or may not be a field. There is only one more property that needs to be checked for it to be a field. If a skew field or a division ring is commutative additionally, if the multiplication is commutative, then of course it's a field. Otherwise it's not a field. Okay, so of course a commutative division ring is a field. Q is an example of a division ring that is not a field, because it's not commutative. And why it's not commutative, that thing we are going to see now. Okay, now after this, the author says that division rings, there are many other examples of division rings which are not commutative, that is, which are not fields. But to present more examples, we need to look at concepts which are far beyond the scope of this book. So we will be going too far afield to present such examples here. However, the study of division rings and the attempts to classify them form an important and almost a central part of algebra. So that thing is there. So now we look at this non-commutativity. Why is this ring non-commutative? And taking our cue from the sixth example, we are going to define some elements in this ring again, just like how we defined E11 star. So define, in this case we will define I star. I star is 0 plus 1i plus 0j plus 0k. Then j star. So in I star, the component of I is 1, the others are 0. Like that, in j star, the component of j is 1, the others are 0, and likewise in k star. So these are quaternions. 0 plus 0 special quaternions. I plus 0j plus 1k. Note that we need not define 1 star, because for us 1 star is nothing but that one unit element. 1 plus 0i plus 0j plus 0k. Now if one actually uses the horrendous definition of multiplication in this ring, one will find these things. I star square. I star square means I star dot I star is equal to j star square is equal to k star square is equal to -1, where this -1 actually means the additive inverse of this unit element. Okay, and along with that, I star dot j star is k star, which is also equal to minus j star dot I star. and like that there are two more. J star dot K star is I star, which is minus K star dot J star, and K star dot I star is equal to J star, which is minus I star dot K star. To remember these products in particular, you can imagine a cyclic structure like this, where you have I star, J star and K star, and where the structure has to be thought of like this. It has an anti-clockwise sense of rotation, so that if you multiply I star and J star, you get K star. If you multiply J star and K star, you get I star. Like that, multiplying K star and I star gives you J star. If you come in the opposite direction, moving clockwise, then you have the negatives of this. That's why I star J star and J star I star are not same, and from there you can conclude that this ring is non-commutative. Okay, and you can pretty much understand that using these elements, a general element like this can be written like this. Okay, where now these additions are not just some symbols, but the actual addition in this ring. And just like the sixth example, using this expression, you can multiply two elements, just like how we ordinarily multiply two algebraic expressions, and you use these rules to collect terms. That's how I wrote this product. So for example, if you look at alpha naught plus b, let me just quickly look at the product. Beta naught plus beta 1 I plus beta 2j plus beta 3 k. Suppose I want to write this term. How do I know these things? You see how j is coming. First of all, if I multiply alpha naught by beta 2, I will get j, alpha naught beta 2j. So that's how I get alpha naught beta 2. Like that, I will get another j by multiplying beta naught by alpha 2j. So plus alpha 2 beta naught j. Then after that, I will get j from I and k, and from k and I. If I multiply k and I, then k star dot I star is j star. That means alpha 3 beta 1. So alpha 3 beta 1, but I star and k star give me minus j star. So minus alpha 1 beta 3, minus alpha 1 beta 3. So that's how we can write the product. Okay, so this is the ring of real quaternions, which is actually a division ring, which is non-commutative, and that's why it's not a field. So here the first section ends, and after this, using these examples, we will define different classes of rings, and then we will start proving results about rings.